Welcome to the deep dive. Sometimes we get access to a document that isn't just news. It's more like a foundational blueprint for an entire field.
Yeah, exactly.
Today, we're cracking open one of those, a confidential briefing document. It's titled the Neurogenesis Funding Plan.
And this isn't just, interesting reading. It's a really comprehensive strategic roadmap. It's from the RIS Neuroregenerative Division, led by Philip Adam Lillian, dated November 2025.
So it's fairly recent.
Very recent.
Mm-hmm.
What we have here is basically a detailed real-time strategy. They're looking at turning the science of neurogenesis, the brain's own power to repair itself, into practical, scalable, regenerative medicine solutions.
And the stakes are clearly high. The core objective, it's right there in the plan. Secure over $1 million in research capital to really drive these solutions forward. What immediately grabbed my attention, though, was the sheer strategic balance of this proposal. It uses this, profound dual strategy.
Absolutely. It's quite clever, actually.
Yeah.
On one hand, they're focusing on immediate translational pathways.
Things like patches and sprays.
Right. Engineered systems like advanced transdermal patches and inhalable sprays that, could potentially hit the market relatively quickly, generate some revenue, prove the concept.
But they don't stop there.
No, not at all. On the other hand, they dedicate significant resources, laying out a visionary framework. They actually term it 22nd century innovations.
Wow. Okay, so really long-term thinking.
Very long-term. It's a document designed to fund both today's product line, essentially, and tomorrow's revolution in brain health.
So for you, the listener, this deep dive is going to be your comprehensive shortcut. We're going past the glossy executive summary.
Like the high-level stuff.
Yeah, and getting straight into the mechanical, the biological, the engineering details outlined in this high-stakes proposal. We want to understand not just what they plan to do, but precisely how they intend to build this future of brain repair and cognitive enhancement.
And to really do that, we have to start at the beginning. We need to look at the biology that makes all of this even possible.
Okay, let's unpack this scientific cornerstone then. When we talk about neurogenesis, we're fundamentally talking about the formation of new neurons, right?
That's it. And the entire premise of this document, this whole funding plan, it rests on the modern understanding of this process.
Which is different from what people used to think.
Oh, completely. It's crucial to remember that for decades, the dogma was that once you hit adulthood, your brain was essentially fixed. No new neurons. Game over.
Right, you just lost them over time.
Exactly. But the foundation of this entire plan relies on the now validated knowledge that neurogenesis is actually a dynamic process. It persists throughout life, even in adulthood.
And that's critical.
It's absolutely critical. This continuous formation of new neurons is essential for the brain's plasticity. That's its ability to change and adapt. It allows us to learn, form new memories, and critically, it offers this amazing potential for regeneration after injury or, age-related decline.
Okay, so if the brain is continuously creating these new cells, where exactly is this happening? The document seems very specific about these neurogenic niches.
It is. The plan identifies two primary neurogenic niches. Think of them as the brain's internal cell nurseries, constantly active.
Okay.
First, there's the subgranular zone, or SGZ. It's located in a part of the hippocampus called the dentate gyrus.
And the hippocampus is all about memory, right?
Exactly. It's the brain's central command post for memory and navigation.
Sure.
So generating new neurons right there.
Yeah.
That directly influences our ability to learn, adapt, remember things. Makes sense.
Okay, so that's one. What's the other?
The second niche is the subventricular zone, the SVZ. This one lines the lateral ventricles, which are fluid-filled spaces deep in the brain.
And cells born there?
They often migrate longer distances. Some turn into specific types of support cells, glia, or interneurons, kind of like connector neurons. Some are also destined for the olfactory bulb, which actually influences our sense of smell.
Interesting. So different roles depending on the niche. But what's fascinating, and the plan details this, is that just having these stem cells sitting there isn't enough. There's a whole process, right? A sequence of steps a cell has to go through.
Oh, absolutely. It's a rigorous 4-stage process that a cell must complete before it actually becomes a functional contributing neuron. It's like a biological assembly line.
Walk us through that assembly line. What's step one?
The first stage is proliferation. This is basically the multiplication phase. The neural stem cells and progenitor cells that live in those niches, they start dividing rapidly.
Just making more potential building blocks.
Exactly, increasing the pool. And this phase is highly sensitive to external inputs, signals from the environment, hormones, etc.
Okay, step two.
Next comes differentiation. The newly proliferated cells, those progenitor cells, they need the right signals to commit to a specific neural fate.
Like choosing a career path.
Yeah, kind of. They differentiate into specialized cells, mostly neuroblasts, which are basically immature neurons. They're on their way, but not functional yet.
Got it. Then what?
Stage 3 is maturation. This is where the cell really starts looking and acting like a neuron. The neuroblast develops its functional anatomy. It grows its long axon for sending signals.
And dendrites for receiving them.
Exactly. And crucially, it starts to establish synaptic connections, preparing to talk to other neurons.
Okay, so it's built itself, it's reaching out. What's the final hurdle?
And this is arguably the most challenging stage, integration. The matured neuron has to successfully weave itself into the incredibly complex pre-existing neural circuitry.
It needs to find its place in the network.
Precisely. It needs to establish functional communication with its neighbors, start contributing meaningfully to the network's processing. It's not easy. And if a new neuron fails to integrate properly,
What happens?
it often undergoes apoptosis,
Right.
programmed cell death, gets cleared away, survival of the fittest, or maybe the best connected.
That seems like an enormous amount of control the body exerts over this. It's not just making cells willy-nilly.
Not at all. Highly regulated.
And the RES plan confirms this process is highly malleable, right? Responsive to specific factors. What are the key dials they're planning to turn with their therapies?
Yeah, they categorize the factors quite broadly, but the specific examples they give are really key to understanding their intervention strategy, how they think they can boost this process.
Let's start with the external stuff, environment and lifestyle.
Okay, so under environmental and lifestyle factors, the proposal goes beyond just, eat well and exercise, although those are there.
Of course.
They cite things like environmental enrichment, stimulating surroundings, consistent physical activity, especially aerobic exercise, and cognitive stimulation, learning new things, challenging your brain, activities that really put demand on the hippocampus.
Standard advice, but important. What else?
They also get into some more specific metabolic interventions, things like intermittent fasting and caloric restriction.
So affecting cell metabolism directly.
Exactly. These are known to optimize cellular resilience and autophagy, those cleanup mechanisms in cells. They also mention meditation, probably for stress regulation.
Stress is bad for neurogenesis, right?
Very bad. Cortisol, the stress hormone, is a known inhibitor. Then they mention, and this is fascinating, controlled exposure to intermittent hypoxia.
Brief periods of low oxygen. That sounds counterintuitive.
It does, but it's used in some rehab contexts. The idea is that brief regulated oxygen restriction can trigger adaptive responses in the brain.
Like a what doesn't kill you makes you stronger kind of signal.
Sort of, yeah. The brain interprets that brief stress as a signal to repair and optimize itself, potentially boosting growth factors. They also mention specific light and sound exposure protocols.
Wow. Okay. So using sensory input too.
Potentially powerful non-pharmacological triggers for some of these neuronal growth pathways.
Okay, so that's the lifestyle side. What about the internal controls, the stuff they plan to deliver with the patches and sprays?
Right, the biochemical factors. This is where their therapeutics come in most directly. First and foremost are the neurotrophic factors.
Brain fertilizers, basically.
That's a great way to put it. Proteins that act as fertilizer for neurons. The plan specifically highlights BDNF, brain-derived neurotrophic factor. That was huge for CNS plasticity, learning, memory.
What others?
Also NGF, nerve growth factor, and GDNF, glial cell line-derived neurotrophic factor. They have slightly different roles, so a combined strategy might be needed. NGF is often more involved with sensory and peripheral neurons, while BDNF is really central to the hippocampus.
And beyond growth factors, hormones, neurotransmitters.
Yes, the plan emphasizes the delicate balance regulated by hormones. We mentioned cortisol being inhibitory during high stress. Estrogen and testosterone often have protective or proliferative effects. It's complex.
And neurotransmitters.
Key ones like serotonin, dopamine, and glutamate. They regulate mood, reward, learning, excitation, all of which directly influence the rate of proliferation and the success of maturation and integration. It's all interconnected.
So it's clearly not just a matter of adding a squirt of BDNF. You need the whole environment to be right.
Exactly. You need the whole chemical milieu to be conducive to new cell growth and survival.
Which brings us to the state of the brain itself, the pathophysiology. What about things like inflammation?
This is probably the biggest strategic challenge they face.
Yeah.
The plan highlights that the brain's own immune cells, called microglia, mediate inflammatory signals.
And inflammation can be good or bad.
It depends entirely on the context.
Mm-hmm.
Acute, short-term inflammation can actually be reparative It can promote neurogenesis as part of a healing response, but chronic low-grade inflammation, that's destructive. It inhibits neurogenesis.
And the goal of the RIS therapies.
A key goal of many ingredients in their proposed stacks is to mitigate that chronic destructive inflammation, to create a more supportive environment.
And why is all this so important strategically? Why the million-dollar funding push?
Because disruption of this dynamic neurogenesis process is directly linked to major debilitating neurological and psychiatric disorders. The plan explicitly connects impaired neurogenesis to the causes or progression of major depression, the cognitive decline seen in Alzheimer's disease, and even certain forms of epilepsy.
So fixing or boosting neurogenesis could be therapeutic for these conditions.
That's the hope. This strong correlation is precisely why developing targeted therapies for neurogenesis is viewed as this multi-million-dollar imperative. The potential impact is huge.
Okay, that detailed scientific foundation makes the biological targets really clear. Now let's talk strategy. If the goal is to deliver these delicate factors proteins, modulators, the number one hurdle has got to be delivery, right? How do you get these complex molecules across really tough biological barriers like skin or the blood-brain barrier?
You've hit the nail on the head. That is the primary hurdle. And the RIS Neuroregenerative Division Plan outlines 3 radically different yet potentially complementary approaches. Each one is designed to overcome a specific delivery challenge non-invasively if possible.
3 approaches.
Yeah. They're basically attacking this from the skin, the lungs, and even the gut.
Okay, let's start with what sounds like the most complex and technologically integrated solution, those advanced transdermal patches. Hashtag tag 2.1 advanced transdermal patches, the integrated solution.
Yeah, as you said, these are definitely not your standard nicotine patch. The core engineering challenge here is getting past the stratum corneum.
That tough, dead outer layer of skin.
Exactly. It's designed to keep things out. So the plan proposes integrating multiple technologies: physical force, structural bypass methods, and chemical assistance all in one patch.
Let's dig into the physics first. How are they physically pushing things through?
Okay, the physical enhancement methods they cite are really next-generation stuff. They're embedding active mechanisms right into the patch itself to literally drive the therapeutic compounds through the skin.
Like what?
The first technology is endophoresis. This involves tiny embedded electrodes in the patch applying a small, very precisely controlled electrical current across the skin.
And the electricity does what?
It provides the driving force. It works mainly through 2 mechanisms. First, electrorepulsion. If your therapeutic molecules have an electrical charge, which many proteins and peptides do,
the current pushes them away?
Right. If the electrode has the same charge, it repels the molecule, pushing it into the deeper skin layers. Second, there's electroosmosis. The current also induces a kind of fluid flow through the skin's natural pores and pathways, and this can help drag uncharged molecules along with the flow.
That's clever.
And the engineering detail here is crucial. The proposal specifies that these patches need programmable current intensity and, really importantly, safety features. They mention using real-time skin impedance sensors.
To measure skin resistance.
Yeah. So the patch can adjust the current automatically to prevent local irritation or burns. It makes it a smart device, adapting to your individual skin.
Okay, electrical force. But they don't stop there. They're combining that with mechanical vibration, sonophoresis.
Correct. Sonophoresis. This uses miniature ultrasonic transducers also embedded in the patch.
Like tiny speakers.
Kind of, yeah, emitting low-frequency ultrasound waves. These waves are specifically tuned to temporarily disrupt the structure of the skin barrier.
How does ultrasound disrupt the skin? What's happening at the micro level?
The waves generate 2 main mechanical effects. One is cavitation. This is the rapid formation and collapse of tiny bubbles within the skin's fluid and lipid layers.
Creates little disruptions.
Exactly. And the other is microstreaming, which is localized fluid movement around those collapsing bubbles. Together, these effects temporarily increase the fluidity and permeability of the stratum corneum. They basically create transient pathways for the drug molecules to sneak through.
And the plan says combining these is key.
Yes, they emphasize the synergy. Using both iontophoresis and sonophoresis in a single device is expected to maximize penetration efficiency far beyond what either method could achieve on its own, hitting the barrier with both electrical and mechanical force.
Okay, that's the physical push. What about bypassing the barrier structurally? You mentioned microneedles.
Right, so if you can't push through it easily, maybe you can poke tiny holes in it. That's the idea behind the structural and formulation enhancements, specifically microneedles.
These aren't like regular injection needles, right?
No, not at all. These are microscopic structures, often thinner than a human hair. They're designed to painlessly puncture just the tough outer stratum corneum, creating these transient micropores,
Tiny channels.
tiny channels, that lead directly to the living epidermis underneath, where absorption is much better. The plan actually specifies two potential designs.
Okay.
One is dissolvable microneedles. These are made of biodegradable polymers mixed with the drug. They penetrate the skin, and then the needles themselves just dissolve, releasing the payload.
Leaving nothing behind.
Exactly. The other design is hollow microneedles. These act like tiny, microscopic hypodermic needles connected to a drug reservoir within the patch, allowing for a more controlled, possibly sustained, delivery.
And delivering what? These growth factors, they must be delicate molecules. How do they protect them?
That's where sophisticated encapsulation comes in. The cargo itself, these highly sensitive growth factors, enzymes, peptides, needs protection from degradation by skin enzymes or pH changes. The plan mandates using liposomes and nanoparticles.
Tiny bubbles again.
Essentially, yes. Lipid-based vesicles. Think of them as tiny biocompatible bubbles that shield the therapeutic agents. They're often engineered to mimic the structure of our own cell membranes.
Does that help them get in?
Yes, it can improve skin penetration either through membrane fusion, kind of merging with the skin cells, or through endocytosis, where the skin cells actively engulf the nanoparticle package whole. It helps protect the payload and get it inside the cells.
This sounds incredibly high-tech. Are they still using older methods too, like chemical enhancers?
They are. They acknowledge that even with all this physical and structural help, chemical penetration enhancers are likely still necessary to temporarily disrupt the skin's natural lipid structure, make it a bit more permeable.
What kind of chemicals are we talking about?
The three primary enhancers cited are pretty well known in transdermal research. First, dimethyl sulfoxide, DMSO. It's a powerful solvent known for disrupting lipid bilayers and increasing cell membrane permeability.
Okay.
Then there's azone, also known as transcutal. It specifically modifies the way the lipids are packed in the stratum corneum, kind of loosening them up. And oleic acid, which is an unsaturated fatty acid, it fluidizes that lipid matrix, making it less rigid and more penetrable.
And they also need solvents just to dissolve everything in the patch.
Right. To ensure that the complex stack of therapeutic agents is actually dissolved and stable within the patch reservoir, the plan also lists common, high-efficacy solvents like ethanol, propylene glycol, and isopropyl myristate. The level of detail here really underscores the complexity of formulating a stable, effective, high-performance patch. It's not simple. Hashtag tag 2.2 inhalable aerosol sprays. Targeted CNS delivery.
Okay, that's the patch. Shifting focus completely, the second strategy bypasses the skin entirely and targets the lungs. Why look at inhalable aerosol sprays for delivering brain therapies?
Well, the lungs offer a couple of big advantages. First, a massive surface area for absorption. Think tennis court size if you spread it all out. Second, it's highly vascularized, lots of blood vessels right there.
So quick absorption into the bloodstream.
Potentially very quick. And importantly, it minimizes first-pass metabolism in the liver compared to swallowing a pill. Plus, there's intriguing evidence for direct, though complex, neuronal pathways linking the nasal cavity and upper respiratory system directly to the CNS, potentially bypassing the blood-brain barrier to some extent.
Direct nose-to-brain routes.
It's an area of active research, but yes, that's part of the appeal. It offers rapid, non-invasive delivery with potential for direct CNS targeting.
What are the engineering challenges for this route? What format do the drugs need to be in?
Success really depends on particle size and formulation. The therapeutic agents need to be formatted either as aerosolized solutions or dry powders. These need to be compatible with existing delivery devices like meter-dose inhalers, MDIs, the standard puffers,
Or dry powder inhalers.
right, DPIs, or even nebulizers for larger volumes or different formulations. But the real focus in the plan is on the targeting strategies to maximize uptake into the bloodstream or CNS and minimize degradation in the airways.
And how are they planning to improve targeting beyond just getting the particle size right?
Again, nanoparticle encapsulation is vital. Protecting the compounds, optimizing their adhesion, maybe targeting specific cells in the respiratory tract.
Similar to the patches, then.
Similar principles, yes, but they also mention a really sophisticated addition here, exosome-based delivery.
Exosomes, what are those?
Exosomes are tiny vesicles, like little packages, that are naturally secreted by our own cells. They act as natural communicators, carrying cargo like proteins and RNA between cells.
So using the body's own delivery system.
Exactly. Using these cell-derived vesicles as natural nanocarriers offers potential advantages like stealth. The body recognizes them, biocompatibility, and maybe even an intrinsic ability to cross biological barriers more easily. It's cutting edge.
Wow. Anything else for targeting?
They also mention surface modification. This involves coating the nanoparticles or the aerosol particles themselves with specific materials. For instance, mucoadhesive polymers.
You make them stick.
Yeah, to help the particles stick to the moist surfaces of the respiratory tract, giving them more time to be absorbed, or coating them with cell-penetrating peptides to actively help them get inside target cells. Hashtag 2.3 innovative probiotic formulations. The gut-brain axis.
Okay, patches for the skin, sprays for the lungs. The third delivery system is maybe the most indirect. It involves the gut. How does that work for the brain?
This approach leverages the well-established connection called the gut-brain axis. The idea is to modulate brain health and potentially neurogenesis indirectly by influencing the gut microbiome.
Through probiotics.
Yes, but not just any probiotics. This strategy combines traditional probiotic science with, again, cutting-edge synthetic biology. The methodology starts with identifying and selecting specific probiotic strains that already have some documented links to improve brain function, maybe reduce brain inflammation, or even effects on neurogenesis itself.
Does the plan name any specific strains they're interested in?
It does. They specifically cite 2 robust, well-studied strains, Lactobacillus rhamnosus GG and Bifidobacterium brief. These are known for their resilience in the gut and their capacity to influence gut health, which in turn influences brain function through various pathways: immune, neural, endocrine.
But the RAS plan isn't just about selling high-end yogurt, right? You mentioned synthetic biology. They're engineering these strains.
That's the really innovative part. The engineering goal is quite ambitious. They aim to use synthetic biology techniques to turn these common probiotic strains into tiny living pharmaceutical factories right inside your gut.
Factories producing what?
The plan is to engineer them to overexpress neurotrophic factors, like producing extra BDNF right there in the intestine, or, alternatively, to significantly boost their production of beneficial neuroactive metabolites.
What kind of metabolites are we talking about?
Primarily, short-chain fatty acids, SCFAs. Things like butyrate. These are produced when gut bacteria ferment fiber, and they're crucial signaling molecules. They help maintain gut barrier integrity, reduce inflammation systemically, and can even influence blood-brain barrier permeability and brain inflammation directly.
So, influencing the brain by producing these fatty acids.
That's one key mechanism. They also target the enhanced production of certain neurotransmitters, like GABA or serotonin precursors, which can be synthesized or influenced by the gut microbiome and potentially signal to the brain via the vagus nerve or other pathways.
Okay, but for this to work at all, these engineered bacteria have to survive the journey through the stomach, right? It's pretty acidic in there.
Survival is absolutely critical. If the engineered bacteria die in the stomach acid, the whole expensive technology is basically wasted.
So how do they protect them?
That's why the plan specifically allocates resources to advanced microencapsulation technologies, essentially creating protective shells or coatings around the engineered probiotics.
Little spacesuits for bacteria.
Something like that. These shells ensure they survive the extremely acidic environment of the stomach and reach the intestines relatively unharmed. There, they can colonize, multiply, and start producing the desired neurotrophic factors, or SCFAs, exerting their therapeutic effects.
That's an incredible level of specificity across 3 completely different delivery platforms: skin, lungs, gut. It really shows they're thinking broadly about overcoming the delivery problem.
Absolutely. It's a multi-pronged attack.
So now that we know how they plan to deliver the medicine, let's look at what they are actually loading into these high-tech patches, sprays, and probiotics. What's inside? Given the complexity of these delivery systems, the formulation, what goes inside, and the manufacturing processes must be just as rigorous, right? Let's start with the ingredients. What's in these stacks? Hashtag 3.1 therapeutic payloads and component stacks.
Right. The plan is very clear that they're deliberately avoiding a single-agent approach. It's all about synergistic blends or stacks designed to hit multiple stages of neurogenesis at the same time.
Covering all the bases.
Exactly. From stimulating proliferation to helping maturation and integration to controlling inflammation, they're looking for combinations that work better together than any single ingredient would alone.
So what are the foundational core bioactive agents that form the basis of these stacks?
They're grouped by function in the document. First, you have the essential neurotrophic factors we already discussed, the brain fertilizers.
BDNF, NGF, GDNF?
Precisely. These are the direct growth signals. Second, they include stem cell growth factors. These are factors that specifically stimulate those precursor cells in the niches to start dividing and proliferating.
Making more raw material.
Exactly. Examples they give include FGF, fibroblast growth factor,
Yeah.
EGF, epidermal growth factor, and IGF, inflin-like growth factor, different factors to kickstart the process.
Okay, growth signals and proliferation boosters. What else?
Third, and this is strategically crucial for survival and integration, are the anti-inflammatory and neuroprotective agents. These ingredients aim to create a healthier, less toxic, less inflamed environment in the brain for the new neurons to actually survive, mature, and connect properly.
Makes sense. What kind of agents are we talking about?
Key examples cited are things like curcumin from turmeric, resveratrol from grapes, vitamin E, and glutathione, a major intracellular antioxidant. Basically, agents known to combat oxidative stress and inflammation.
Okay, that covers the core proteins and protective elements. But the plan then outlines 2 specific nutritional and maybe pharmacological stacks. These seem designed more for consumer product applications, probably for the patches and sprays initially.
That seems likely. These stacks represent that multi-component synergy they're aiming for, trying to support the entire neurogenesis pipeline from different angles, using things that might be deliverable with current or near-term tech.
What's in the main neurogenesis stack?
This one is highly comprehensive. It seems focused on boosting proliferation, but also overall neural health and function.
Right.
It includes well-known adaptogens and nootropics like lion's mane mushroom, Bacopa monnieri, and ginkgo biloba.
Things people might already be taking for brain health.
Exactly. It also mandates high levels of omega-3 fatty acids, crucial for cell membranes, polyphenols, often specifying green key extract as a source, essential B vitamins, specifically B6, folate, B9, and B12, which are critical for methylation cycles and neurotransmitter synthesis. Also vitamin D, magnesium, zinc, and choline. It's a very broad spectrum.
That list is extensive. It covers a lot of metabolic and structural ground. But you mentioned pharmacological too. The most interesting inclusion, perhaps, is the mention of cannabinoids. Was that in this stack?
Yes. It is a critical strategic conclusion mentioned right alongside those other components. The plan specifically notes the potential neuroprotective and neurogenesis-promoting effects of certain cannabinoids.
So things like CBD or maybe other compounds.
The document doesn't specify exactly which ones, likely due to the complexity, but it acknowledges the need for ongoing research and, of course, navigating the potential regulatory complexities. But their inclusion strongly suggests that the RIS division views these compounds as potentially indispensable for maximizing the stack's overall efficacy. They're not ignoring that whole area of pharmacology.
Okay, that's the neurogenesis stack. What about the second one mentioned, the stem cell generation stack? What's its specific purpose?
This stack seems more tailored toward supporting the physical generation and viability of the stem and progenitor cells themselves. It's highly focused on powerful antioxidants and general regenerative promoters.
Like what ingredients?
It features things like blueberry extract and spirulina, both known for very high antioxidant capacity. Also, astaxanthin, another potent antioxidant. Quercetin, found in onions and apples. Ginseng, an adaptogen with regenerative properties. Vitamin C, essential for collagen and an antioxidant. And melatonin.
Melatonin, isn't that just for sleep?
It's well known for sleep regulation. But it's also a remarkably potent free radical scavenger and has documented protective effects on stem cell integrity and mitochondrial health. So its inclusion here likely targets that protective viability-enhancing role for the stem cells. Hashtag tag 3.2 advanced manufacturing methodologies. GMP focus.
Okay, so you have these complex stacks with delicate proteins, growth factors, vitamins, plant extracts, maybe even cannabinoids, and you need to load them into these equally complex delivery systems with electronics. The manufacturing must be incredibly challenging. It's less like bottling pills and more like building microchips, maybe?
That's a really good analogy, especially for the patches. The plan emphasizes that the process demands adherence to the absolute highest good manufacturing practice (GMP) standards, precisely because they're integrating active electronic components with pharmaceuticals. It's a medical device hybrid.
So how do they actually build these advanced transdermal patches? What's the process?
It starts with layer-by-layer assembly. These patches aren't just mixed together, they're constructed sequentially. Building up the backing layer, then maybe a flexible circuit board layer, the drug reservoir, the adhesive layer, often done in highly controlled clean room environments.
Layer by layer. What about getting the drugs and electronics in there accurately?
Crucially, the plan indicates they'll rely heavily on specialized printing technologies. Think adaptations of standard inkjet or screen printing, but optimized for much higher precision in different materials.
Printing what exactly?
Printing multiple elements precisely onto the layers, the therapeutic drugs themselves, often in specific patterns or locations. The conductive inks, like silver or carbon, needed to create the electrodes for iontophoresis, and potentially even printing the specialized materials that form those miniature ultrasonic transducers for sonophoresis.
So they're literally printing the drugs and the functional electronic components.
That seems to be the approach, yes. Precision printing is key for ensuring accurate dosage and making sure all the electronic parts are functionally connected.
Wow. What other tech is needed?
That level of precision requires microfabrication techniques, methods often borrowed from the semiconductor industry, like photolithography or micromolding. These are needed to create the microscale features within the patch structure.
Like what kind of features?
Think the tiny reservoirs that hold the drug, the microscopic channels that might feed the drugs to the microneedles, or the structures needed for the iontophoresis system to work correctly.
And finally, you have to put all the electronics together.
Exactly. The electronics integration, the control circuits, the tiny batteries or maybe wireless power receivers, the skin impedance sensors, we talked about all these, must be flexibly and durably embedded into the patch structure. They have to survive being worn on the skin, maybe bending, and still function reliably to enable that real-time feedback and programmable intensity.
And all that complexity is what drives the cost up, presumably.
Absolutely. That's why they estimate that high manufacturing cost per unit. It's a sophisticated piece of miniature engineering.
Okay, shifting to the inhaler sprays. The manufacturing challenges there seem different. Less about integrating electronics, more about the particles themselves.
Exactly. For the sprays, the manufacturing is dominated by physics and precision powder or liquid engineering. They need highly controlled aerosolization processes.
How do they make a spray?
For the meter dose inhalers, the PMBIs, it involves precisely mixing the drug with the propellant in a pressurized canister. For dry powder inhalers, the DPIs, it requires techniques like spray drying or micronization.
Grinding it down.
Yes, grinding or using specific precipitation methods to synthesize the drug particles into the perfect size range. Typically, that's between 1 and 5 microns in diameter.
Why that specific size?
It's the sweet spot.
Yeah.
Small enough to get carried deep into the lungs with inhalation, but large enough to avoid being immediately exhaled again. It optimizes deposition in the peripheral airways where absorption is best.
And how do they make sure every puff is the same? That seems critical for dosing.
Absolutely critical. Stringent quality control is non-negotiable, as the plan states. This involves constant in-process particle size analysis using techniques like laser diffraction, testing the aerosol performance, how the plume develops, its velocity, and rigorously verifying content uniformity to guarantee that every single actuation, every puff, delivers a consistent, effective dose of those potentially very expensive therapeutic payloads. Yeah. You can't have variation when you're dealing with potent brain-active compounds.
Okay, that manufacturing strategy for both patches and sprays provides a clear, though complex, path to market for these near-term products. But as you said earlier, the plan doesn't stop there. It projects far, far beyond 2025. It gets into stuff that sounds like pure science fiction.
It really does. This transition in the document is fascinating. The RIS plan clearly allocates a portion of its long-term strategic thinking and presumably future funding requests to concepts that are currently purely visionary. They require fundamental breakthroughs in physics, material science, biology.
This is the 22nd century innovations part.
Exactly. This is the blueprint for the eventual, maybe ultimate, forms of neural intervention they envision.
Okay, let's dive into this future vision, starting with nanotechnology and bioelectronics. If the patches we just discussed are maybe the first or second generation, what are the theoretical fifth or sixth generations of brain interface, according to this plan?
Well, the plan projects devices that would completely overcome the challenges of crossing the blood-brain barrier non-invasively. The ultimate dream devices here are brain-embedded nanobots.
Actual tiny robots inside the brain.
That's the concept. Nanoscale robots, potentially self-powered or remotely powered, capable of navigating through the cerebral vasculature, actively crossing the blood-brain barrier, and traveling directly to specific targets, like those neurogenic niches in the SDZ.
And what would they do there?
They could deliver payloads like growth factors with incredible precision, maybe remove harmful protein aggregates, or even mechanically stimulate neurogenesis or synaptic plasticity right at the source. Ultra-high precision intervention.
Okay, that's nanobots. What about other bioelectronics?
Alongside that, they envision much more sophisticated bioelectronic devices than we have today. These might be implants, perhaps designed to be non-invasive or temporary. that deliver highly optimized electrical or magnetic stimulation patterns.
Optimized how?
Tailored by AI, potentially in real time, based on brain readings, to induce neurogenesis specifically in targeted regions, maybe without needing systemic drugs at all. Purely informational or energy-based therapy.
This moves beyond just delivering stuff, though. It gets into directly manipulating the biological code itself using genetic and cellular engineering.
Exactly. The plan explicitly cites the potential of gene editing, specifically mentioning the revolutionary tool CRISPR-Cas9.
How would they use CRISPR for neurogenesis?
The application envisioned would be to use CRISPR, perhaps delivered via viruses or nanoparticles, to directly edit the genes within neural stem cells or other relevant brain cells. The goal would be to enhance the expression of genes already known to be critical for neurogenesis, genes involved in proliferation, migration, survival, or integration.
So basically reprogramming the brain's own cells to be better at repair.
That's the idea. Optimizing the brain's internal genetic programming for regeneration.
And once you've potentially edited the cells, how would you control their activity with precision?
That's where optogenetics comes in. This is a technique that's already used extensively in research. It involves introducing light-sensitive proteins, called opsins, into specific types of cells, say, neural stem cells in the SGZ.
Making them responsive to light.
Exactly. Then, by shining specific wavelengths of light onto those cells, often delivered via implanted optical fibers or perhaps future microscopic light sources, researchers could literally turn the activity of those specific cells on or off with millisecond precision.
So you could precisely stimulate proliferation or maturation just in the cells you've targeted.
Precisely. It offers unprecedented spatial and temporal control over neural activity, far beyond what electrical stimulation or drugs can typically achieve. You could potentially stimulate neurogenesis just when and where it's needed.
That's incredibly precise control over existing cells. What about replacing large areas of damage, like after a stroke?
For large-scale physical repair, the plan looks towards 3D bioprinting.
Print brain tissue.
That's the long-term vision. This involves using specialized 3D printers that use bioinks, inks containing living cells like neural stem cells, neurons, glial cells, mixed with hydrogels or scaffold materials.
And they print.
They print customized, three-dimensional neural tissue constructs, potentially mimicking the architecture of the damaged brain region. These engineered tissue constructs could then, theoretically, be surgically implanted into areas of the brain damaged by stroke, traumatic injury, or neurodegeneration.
Acting like a living patch or scaffold for repair.
Exactly. Providing a ready-made environment containing the right cells and structural cues to promote repair and integration with the host brain tissue.
Okay, nanobots, gene editing, optogenetics, bioprinting. Now we get into what sound like the most theoretical concepts in the whole plan, advanced brain interfaces. What's beyond just reading brain signals?
This is where we move towards optimizing the input-output relationship with the brain in a much more sophisticated way. They envision brain-computer-brain interfaces, BCBIs.
Brain-computer-brain, not just brain-computer.
Right. Unlike traditional brain-computer interfaces, BCIs, that primarily read information out of the brain to control external devices, BCBIs are bidirectional.
Yeah.
They would not only read the state of the brain, perhaps monitoring activity in the neurogenic niches or markers of inflammation, but also deliver optimized, real-time stimulation patterns back into the neural network.
Creating a closed loop.
Exactly. A closed-loop system where the interface monitors the brain's state and continuously adjusts its stimulation output to optimize a desired outcome, like maximizing neurogenesis or reducing seizure activity, adapting moment by moment.
And then there's the most speculative concept of all mentioned in the plan, the quantum neural interface. What on earth could that possibly mean?
Okay, yeah, this is truly pushing the boundaries. Venturing into territory where neuroscience meets fundamental physics, it suggests moving beyond classical physics, beyond just manipulating electrical signals or chemical concentrations.
So what does it propose?
The quantum neural interface is hypothesized very speculatively to use quantum phenomena or properties perhaps influencing quantum coherence in microtubules or entanglement between particles or manipulating quantum tunneling effects at synapses to interact with neuronal activity.
At a submolecular level.
Potentially, yes. The idea, however theoretical, is that influencing these quantum effects could allow for ultra-high precision manipulation of neuronal computation and brain health at a scale far smaller and more fundamental than even today's most advanced bioelectronics allow.
That sounds almost philosophical, influencing the quantum underpinnings of thought.
It borders on that, yes. It's definitely blue sky thinking, But its inclusion shows the sheer scope of their long-term ambition to understand and potentially manipulate brain function at its most basic physical levels.
And presumably, none of this high-tech intervention, whether near-term or far future, works without a massive data framework. The plan mentions computational systems biology.
Absolutely. Data is the bedrock, especially for personalization. The plan makes it clear that realizing the potential of these complex interventions depends heavily on utilizing AI and deep learning algorithms.
To do what?
To analyze vast amounts of data genetic profiles, lifestyle data from wearables, biomarker readings, brain imaging, to predict how an individual is likely to respond to a specific neurogenesis stack or stimulation protocol. To personalize the therapy.
Tailoring it to the individual.
Precisely. And they also forecast the advanced application of exosome therapy, building on what we discussed earlier. Imagine using AI to design and engineer exosomes to carry bespoke combinations of neurogenesis-promoting factors, perfectly tailored to a single patient's specific needs based on their real-time biological data. Ultra-personalized nanomedicine.
It's an incredible arc, starting with sophisticated patches and sprays and mapping a path towards quantum-level brain interfaces, all driven by AI and personalized medicine. This is clearly a strategy that moves from immediate integrated product sales towards funding revolutionary, almost unimaginable blue-sky research.
That's the dual strategy in action. Use the near term to fund the far term.
Let's ground this immense ambition back in the reality of the balance sheet. How do they plan to sell this and get the funding?
Okay, so the success of those immediate translational pathways, the patches, the sprays, the probiotics, it really hinges on a robust commercialization strategy. Does the document make a compelling case for the market opportunity? Is there money to be made here?
Oh, definitely. The drivers they cite for the market potential are pretty undeniable and substantial. We're looking at potentially a huge market size.
Driven by what factors?
Several major global trends. First, the undeniable reality of the global aging population. As more people live longer, the prevalence of age-related cognitive decline and dementia just skyrockets. That creates a massive need.
Makes sense. What else? Second, the already high incidence and enormous economic burden of neurological disorders like Alzheimer's, Parkinson's, stroke, depression, epilepsy. The list goes on. Therapies that could even slow progression, let alone regenerate function, would be immensely valuable.
True.
And third, they point to the continuous rise in global healthcare expenditure. Societies are willing to spend more on health, and investors are often willing to back innovative therapies that promise significantly better outcomes than current standards of care, even if they're expensive initially.
So a large unmet need combined with willingness to pay. Who are the immediate buyers they're targeting for those first-generation products, like the advanced patches and sprays?
The plan segments the initial target audiences quite clearly into 4 key demographics.
Okay, who's first?
First, and probably the largest group, is aging individuals, say 50 and older, who are looking for proactive ways to maintain cognitive function, prevent decline, basically neuroprotection as they age.
The anti-aging and wellness market.
Exactly. Second, a highly motivated sector, professionals and students. People looking for a cognitive edge, enhanced focus, improved learning capacity, memory optimization, the performance enhancement market.
But biohacker crap.
Potentially, yes, and just mainstream professionals wanting to stay sharp. Third, the established health and wellness enthusiasts, people who are already investing heavily in supplements, organic food, fitness, mindfulness. They're often early adopters of new health technologies.
And the fourth group?
And fourth, a crucial clinical market, patients and caregivers, people directly dealing with the impact of specific neurological conditions. They and their families are often actively seeking complementary or potentially regenerative therapies beyond standard pharmaceuticals. #tag financial details and funding strategy.
Okay, clear target markets. We mentioned at the start the overall objective is securing over $1 million in initial funding, but the financial details within the document really highlight the extreme cost of developing and manufacturing this stuff.
Yes, that's a critical takeaway when you read between the lines. When we look at the specific manufacturing cost example they provide for the patch, it really tells a story.
What's the number?
They estimate the manufacturing cost per single complex transdermal patch, the one integrating iontophoresis, sonophoresis, microneedles, and the complex formulations could range up to $5 per unit.
$5 just to make one patch.
Per unit, yes.
Okay, let's put that in perspective. A standard non-electronic nicotine patch probably costs pennies to manufacture, right?
Exactly, maybe dimes at most. $5 per unit manufacturing cost. That signals this product is fundamentally being positioned as a disposable medical device, or maybe a cosmeceutical device, not just a simple supplement delivery system.
And that cost is driven by all the integrated tech.
Precisely. It's the cost of the embedded electronics, the specialized printing technologies, the need for GMP-compliant microfabrication, the quality control. All of that adds up significantly. And of course, a $5 cost per unit implies a potentially very high consumer price point will be necessary to recoup the massive R&D investment and make a profit.
They must have a more focused budget for their initial product launch, too.
They do. The plan details a dedicated, specific budget figure of $600,000.
For what exactly?
That $600 is earmarked specifically for the initial launch of a signature Neurogenesis stack, likely delivered via one of the platforms paired with a companion app prototype. That budget is intended to cover final formulation work, perhaps initial small-scale clinical trials or safety studies, the app development itself, and the initial marketing and launch activities.
So a significant chunk of that million-plus goal is just for getting the first product out the door.
Seems that way.
So how does the RES division actually plan to get this million-plus? What are their targeted funding strategy channels?
They're not putting all their eggs in one basket. It's a strategically diversified approach. They're targeting high-value grants from major government and nonprofit research bodies.
Like who?
They mention the National Institutes of Health, NIH, specifically the National Institute of Neurological Disorders and Stroke, NINDS, also the Defense Advanced Research Projects Agency, DARPA, which funds high-risk, high-reward tech, and various small business innovation research, SBIR programs. These grants are non-dilutive funding, which is ideal.
What else besides grants?
They also plan to seek powerful strategic alignment via corporate and academic partnerships. They list potential engagement targets like major pharmaceutical companies. Biogen and Roche are mentioned as examples.
Companies already big in neuroscience.
Exactly. Partnering could bring in funding, expertise, and future distribution channels. They also mention elite academic research centers like Harvard and MIT, possibly for collaborative research, leveraging institutional expertise, and maybe co-funding opportunities.
So grants, big pharma, top universities. What about private investment?
Yes. The remainder of the capital is sought through the more standard routes. Venture capital firms, potentially crowdfunding platforms, maybe for specific product launches to gauge market interest, and philanthropy, targeting foundations interested in brain health or aging. It's a multi-source strategy to de-risk the funding effort. #tag ancillary products, the companion app.
Okay, one last piece of the commercial puzzle they outline is the user experience, which seems built around an ancillary product, a companion mobile application. Why is this app apparently so critical to the overall plan? It got its own budget line item.
It seems critical because it directly connects the high-tech pharmaceutical intervention, the patch or spray, back to all those crucial lifestyle and environmental factors we discussed way back in Section 1.
Closing the loop.
Exactly. The patch or spray might deliver the growth factors, but it works best if the user's brain environment is optimized. The app provides the tools and information to help the user create that necessary supportive environment for success. It makes the product more of a system, less of just a drug delivery device.
What are the key features they plan for this app to optimize the user's neurogenic environment?
The plan outlines several key functions. First, educational content, providing users with accessible, science-backed information, why neurogenesis matters, how it works, how the product ingredients support it, what lifestyle factors are important, building user understanding and compliance.
Makes sense. Okay, what else?
Second, detailed lifestyle tracking tools, monitoring and encouraging those positive modulators we talked about, tracking exercise frequency and type, specific diet inputs like omega-3s or polyphenol intake, sleep quality and duration, making users aware and accountable.
Gamification, maybe.
Possibly. Third, they specifically plan a suite of brain training games, things like memory match, Sudoku, pattern recognition challenges. The idea here isn't just for fun. It's explicitly designed to provide the cognitive stimulation needed to help those newly formed neurons successfully integrate into functional brain networks. Use it or lose it, applied to neurogenesis.
That's clever, linking the games directly to the integration phase.
Exactly. And finally, the app is planned to include mindfulness sessions, guided meditation, breathing exercises for stress reduction, and community forums.
Why forums?
For social support, sharing experiences, maybe accountability groups. Reducing stress and building community are also considered critical for maintaining that optimal biochemical environment needed for new neuron survival and overall well-being.
So the app really does try to cover all the bases, turning an advanced bio device into a more holistic, data-driven lifestyle program.
That seems to be the goal. Maximize the chances of the core technology actually working effectively in the real world. Hashtag tag outro. So if we step back and synthesize this entire plan from Philip Adam Lillian's division at RIS, what we really see is this powerfully comprehensive two-pronged strategy.
Yeah, it starts with a really deep fundamental knowledge of the biology, the SGZ, the SVZ, the stages of neurogenesis.
Right, and leverages that knowledge by creating these synergistic stacks of growth factors, nutrients, anti-inflammatories, neuroprotectants.
And then applies some truly radical delivery engineering, iontophoresis, sonophoresis, microneedles, engineered exosomes, symbio probiotics, all designed to bypass those biological hurdles right now.
Exactly. And that immediate strategy, the integrated patches, the targeted sprays, the engineered probiotics, it seems designed not just for therapeutic benefit or profit.
But as a crucial revenue and validation bridge.
Precisely. A bridge to secure the credibility and, importantly, the capital needed to fund the truly ambitious long-term work outlined in the second half of the plan.
Exploring the frontiers of nanobots, optogenetics, gene editing, bioprinting, and even those far-out concepts like quantum manipulation.
So what this deep dive really provides you, the listener, is a detailed, nuts and bolts look at how a multi-million-dollar research and commercialization strategy is being structured. And it's all built around leveraging and boosting the human brain's own innate but often untapped capacity for self-repair and improvement. The sophistication of the engineering they're proposing for today is already astounding.
It really is. But that vision for tomorrow, for the 22nd century, is frankly staggering. We discussed that ultimate boundary push they mention, the hypothetical quantum neural interface. Now, if the fundamental process of neurogenesis, and indeed all brain function, involves incredibly precise chemical balances and electrical signaling patterns,
Which it does.
and if we project, even theoretically, a future technology that could perceive and influence neuronal activity patterns right down at the quantum level, well, it raises a truly profound question, doesn't it?
It certainly does. What are the ultimate theoretical limits of bioelectronic or maybe even quantum biological manipulation if we gain the ability to influence brain activity and structure at the smallest possible scales, the very foundations of its operation? Are we only talking about repair and treating disease?
Or does that level of control inevitably imply the ability to fundamentally optimize, enhance, perhaps even redesign the very limits of human cognition, memory, creativity?
It really encourages us to consider where that line between healing and enhancement truly lies, or if it even exists when you're potentially dealing with the power to interface with biology at the quantum level.
A fascinating, maybe slightly unnerving future to contemplate. We'll definitely continue tracking developments in this space. Thanks for walking us through this complex document.
My pleasure. Always fascinating stuff.
Until the next deep dive.